Good day, students. Welcome again to our statistics and probability class. But before we'll talk about the normal distribution, we'll have our devotional first. And the message for this moment is heaven's plus sign. Our memory text is found in John 10, verse 10. The thief cometh not but for steal and to kill and to destroy. I come that they might have life and that they might have it more abundantly. A little girl had reached the place in school where she was being introduced to the wonders of arithmetic. Multiplication signs, minus signs, division signs, and plus signs all made a deep impression in her. One day, she was sitting in church with her parents who were members of one of today's popular denominations. She noticed a large gold cross on the altar. Turning to her father, she whispered, "Daddy, what is the plus sign doing on the altar?" The little girl was a bit confused over the difference between a cross and a plus sign. Nevertheless, the cross is without question the greatest plus sign in the universe. Because of the cross, we not only have life, we have it more abundantly. To the death of Christ, we owe even this earthly life. The bread we eat is the purchase of his broken body. The water we drink is bought by spilled blood. Never one saint or sinner eats his daily food, but he is nourished by the body and the blood of Christ. The cross of Calvary is stamped in every leaf. It is reflected in every water spring. The little girl was being initiated into the wonders of arithmetic, saw plus signs everywhere, because her mind was occupied with this mathematical symbol. Person who looks directly at the sun even for a moment sees the outline of the sun on every object on which he gazes for the next few minutes. Thus also the Christian who spends sufficient time contemplating the cross will see its image reflected everywhere, and that image will add a new dimension to life. Work will be a pleasure because it is service for the King. Obedience will bring joy because we love the one said, "Keep my commandments." Sacrifice and self-denial will bring blessings because they enable us to share heaven's gifts with others. Truly, the cross is heaven's plus sign. It makes possible the more abundant life. And now we will be talking about the normal distribution. What is the normal distribution? The normal distribution is a continuous symmetric bell-shaped distribution of a random variable. The graph of this distribution is called a normal curve, and the figure is shown below. The standard normal curve as the model for inferential statistics has the equation y equals e to the power of negative 1/2 times x minus the mean over the standard deviation squared, all over standard deviation times the square root of 2 times pi, where y is the height of the curve for particular values of x is any score in the distribution, and the standard deviation of the population, the mu is the mean of the population, and the value of pi is 3.1416, and the value of e is 2.7183. Now, we have different properties of the normal distribution. The first one is the distribution curve is bell-shaped. Number 2, the curve is symmetric about its center, the mean. Number 3, the mean, the median, and the mode coincide at the center. Number 4, the width of the curve is determined by the standard deviation of the distribution. Number 5, the tails of the curve flatten out indefinitely along the horizontal axis, always approaching the axis but never touching it. That is, the curve is asymptotic to the baseline. And number 6, the area under the curve is 1. Thus, it represents the probability or proportion or the percentage. Okay, next. we have the distribution of area under the normal curve. It is also known as the empirical rule, or the 68%, 95%, and 99.7% rule. The area under the part of a normal curve that lies within one standard deviation of the mean is approximately 0.68 or 68%. Within two standard deviations, about 0.95 or 95%. And within three standard deviations, about 0.997 or 99.7%. Okay, this is the illustration of what we have discussed the previous slide of the distribution of area under the normal curve. So as we have noticed that the normal curve, the center is the mean, and going to the right are all positive, and going to the left are all negative. And we have from the -1 to +1, that is about 68%, and -2 to +2, that is about 95%, and from -3 to +3, that is about 99.7%. We have the standard normal distribution of a random variable. It's a normal distribution with mean 0 and standard deviation 1. The letter Z is used to denote the standard normal random variable. The specific value Z of the random variable Z is called the Z-score. We will talk about that later, about the Z table. Now we have the probability of a random variable Z with the standard normal distribution is given by y equals the P of Z is equal to 1 times e to the power of -z squared over 2 divided by the square root of 2 pi. Okay, this is the graph of the standard normal distribution. So you have to observe. Remember, the area is equal to 1. And at the center is 0. And that's the mean. Going to the right, we have +1 to 3. And going to the left, we have -1, -2, -3. And they are called the Z-score. The table of areas under the normal curve is also known as the Z table. That is, in your module, the values of the Z table. The Z-score is a measure of relative standing. It is calculated by subtracting the mean from the measurement X and then dividing the result by the standard deviation. The final result, the Z-score, represents the distance between a given measurement X and the mean, expressed in standard deviations. The standard normal distribution table to be used in this course gives areas under the standard normal curve for the variable Z, ranging from 0 to a positive number Z. So from 0 to the right, they're all positive, and from 0 to the left, they are negative. In the table, the area A gives the probability that the value of Z lies between 0 and a constant Z. So this will be the notation. A is equal to the probability that Z is greater than 0 but less than the positive Z. Okay, there are 4 steps that we're going to consider about the process in finding the areas under the normal curve given a Z value. Step 1, express the given Z value into a 3-digit form. Number 2, using the Z table, find the first 2 digits on the left column. Step 3, match the 3rd digit with the appropriate column on the right. Step 4, read the area or probability at the intersection of the row and the column. This is the required area. So those are the 4 steps that you're going to follow in finding the areas under the normal curve given a z value. Okay, example. Find the area that corresponds to z is equal to 1.36. We have steps in solution. There are 3 steps that we are going to follow here. We have number 1, express the given z value as a 3-digit number. So z equals 1.36. So already a 3-digit number, so as is. Number 2, in the table, find the row z is equal to 1.3 and find the column with the heading 0.06. And number 3, read the area or probability at the intersection of row 1.3 and column 0.06. And this area is 0.4131, and this is the required area. So that is how to find the area corresponding to some values of z. Okay, like this. Find the area that corresponds to z equals 1. So we will go to z that is 1.0 and another value that is 0.00. And the intersection is 0.3413. So the area of z equals 1, that is 0.3413. Okay, find the area that corresponds to z equals 2.58. So you will go to 2.5 and then 0.08. So the area is 0.4951. Okay, we have the fact. The area between 0 and positive value z is the same as the area between negative z and 0. To find the area between negative z and 0, use the value in the table corresponding to positive z. So if there will be a given area that is negative, it's the same value with those positive at the z table. So you have to do the same process on how to get the area using the positive in getting the area of negative z. Okay. The area that corresponds to z equals 2.58 is the same as the area that corresponds to z equals negative 2.58. So the same value with positive 2.58. And the area is 0.4951. Okay, find the area that corresponds to z equals negative 1.15. So you will go to positive 1.1 and 0.05. That's the required area is 0.3749 because that's the intersection. Okay, what is the probability that the value of a standard normal random variable z lies between 0 and 1.20? So the area is 0.33, that is 0.3997, and from negative 2.7 and 0, or between negative 2.07 and 0 is 0.4808. The steps will be explained later. So we will go to understanding the z-scores. The areas under the normal curve are given in terms of z values or scores. The z-score locates x either within a sample or within a population. Now we have 2 formulas here. The formula for calculating z is z equals x minus mu, which is the mean, all over the standard deviation. That is the formula if the z-score for population data. And the second is z equals x minus the sample mean all over the sample standard deviation. If we're going to have the z-score for sample data, where x there is the given measurement, the mu is the population mean, the x there is the sample mean, and Here is the population standard deviation, and S is the sample standard deviation. So you have to take note of these two formulas in getting the z-values or the z-score. Okay, example, given the mean 50 and the standard deviation 4 of the population of reading scores, find the z-value that corresponds to score x equals 58. So we have 4 steps to follow. Number 1, use the computing formula for finding the z-score of population data. We have to use the first formula. We have z is equal to x minus the mu or the mean all over the standard deviation. To check the given values, since these are population values, the z-score locates x within a population. So we have our mean 50 and our x is 58. The x there is the score, the reading score. Step number 3, substitute the given values in the computing formula. So we have z is equal to 58 minus 50 divided by 4. And the last step is compute the z value. So we have 58 minus 50 is 8, divided by 4 is 2. Thus, the z value that corresponds to the raw score 58 is 2 in the population distribution of reading scores. Okay, next example, we have scores in a science test. So given we have x is 20 and the S or the sample standard deviation is 4, and we have the sample mean that is 26. And we will compute the corresponding score. So we have step number 1. Use the computing formula for finding the z-score of sample data. So we will use the second formula since the given there, the sample, the standard deviation, and the sample mean. So we have z is equal to x minus the sample mean all over the sample standard deviation. So we check the given values. Since these are sample values, the z-score locates x within a sample. So sample mean is 26, the sample standard deviation is 4, and the x or the score in a science test is 20. So substitute the given values in the computing formula. So we have z is equal to 20 minus 26 divided by 4. Compute the z value. 20 minus 26 is negative 6 divided by 4 is negative 1.5. Since negative divided by positive is negative. Thus, the z value that corresponds to the raw score 20 is negative 1.5 in the population distribution of science scores. Okay, we will go to determining probabilities. There are 3 notations for a random variable. Number 1, we have the probability or P, that is Z is greater than A but less than B, denotes the probability that the Z score is between A and B. Second, P of Z that is greater than A denotes the probability that the Z score is greater than A. The third, P of Z less than A denotes the probability that the Z score is less than A, where A and B are Z score values. Okay, you look at those illustration or the figures and finding the areas of other regions. So the first 2 figures, we have tails, right of a positive Z or left of a negative Z. So those are the form of the graph. In the next two figures, we have between two z values with the same sign. It's either all are negative or all are positive. Next, we have here between two z values with opposite signs. So if there will be negative and positive z values, so your graph will look like this. And we have the cumulative left of a positive z or right of a negative z. So if we will say to the right of negative z, so your shaded region will be going to the right. And if we will say below positive z, so your shaded region will be going to the left side. Okay. We have 4 cases in finding areas of other regions. We have case number 1, the region involved. We have tails right of a positive z or left of a negative z. Okay, that's the illustration. Case 2, between two z values with the same sign. So it's either both values are positive and both values are negative. So that's the illustration of the graph. Number 3, between two z values with opposite signs. So it's either negative or positive. And number 4, we have cumulative left of a positive z or right of a negative z. So it's either, we will say, to the right of a certain z or to the left of a given z. So we will go to case 1, finding areas of region details. To find the area at any tail, look up the z-score to get the area. Then subtract the area from 0.5. So 0.5 is a constant where you will subtract or you will add. So in this case, z, positive z to the right or negative z to the left, you have to subtract the area from 0.5. Okay, you have to take note of this phrases where z is greater than a. They have the same meaning. If we will say greater than z, at least z, more than z, to the right of z, above z. So they have the same meaning. We will go to the right. Okay, example, find the area greater than z equals 1. There are 7 steps that you are going to follow. Number 1, draw a normal curve. Number 2, locate the z value. So the z value is 1, so you have to locate that is at the positive area. Then draw a line through the z value. So you have to draw a line from the positive. You shade the required region. Since greater than z equals 1, so you have to shade going to the right of positive 1. Number 5, consult the z table and find the area that corresponds to z equals 1. So if we will use the z table, the z equals 1 corresponds to an area of 0.3413. Number 6, examine the graph and use probability notation to form an equation showing appropriate operation to get the required area. So the graph suggests subtraction since that is going to a positive number going to the right. And the required area is equal to 0.5 minus 0.3413, and that is 0.1587. That is the probability of z that is greater than 1 is 0.1587. The last step is make a statement indicating the required area. The proportion of the area greater than z equals 1 is 0.1587. Okay, note the area under the standard normal curve for z greater than 2 or to the right of 2 is the same as the area for z less than negative 2 or to the left of negative 2. They have the same value, that is 0.4772. So we will still subtract because that is to the left of negative 2. So 0.5 minus 0.4772, that is 0.0228. That's the required area. Okay, find the area to the left of z equals negative 1.5. So in looking the value in the z table, it's the same with positive 1.5 and the area is 0.4332. So we still subtract 0.4332 from 0.5 and the required area is 0.0668. Okay, example, find the area to the left of z equals negative 1.5. I just repeated the example a while ago. And we have to follow the 7 steps. Number 1, draw a normal curve. Number 2, locate the z value, and that is negative 1.5. So that is at the left side of the graph of the normal curve. Then you shade the required region to the left of z, meaning you're going to shade from negative 1.5 to the left side. Consult the z table and find the area that corresponds to z equals negative 1.5. It's the same with positive 1.5, and the area is 0.4332. Examine the graph and use probability notation to form an equation using or showing appropriate operation to get the required area. And we still subtract 0.5 minus 0.4332, and that is 0.0668. So the P, or the probability of z that is less than negative 1.5 is 0.0668. And make a statement indicating the required area. The proportion of the area to the left of z is, that is negative 1.5, is 0.0668. Okay, find the area below z equals 1.5. So 1.5, first we will draw a normal curve, then locate the z value. 1.5 is at the positive side, as the right side of the graph of the normal curve. And then we will draw a line through the z value and shade the required region. Since below z, below z equals 1.5, so we will go to the left side of 1.5 and we'll shade all the region. Then consult the z table and find the area that corresponds to z equals 1.5, and that is 0.4332. You examine the graph and use probability notation to form an equation showing appropriate operation to get the required area. And this time, it suggests addition since our shaded area is more than half. So we will add 0.5 plus the area of z 1.5. So 0.5 plus 0.4332, that is 0.9332. That is the probability that z, or z is less than 1.5 or below z 1.5, that is 0.9332. Make a statement indicating the required area. The proportion of the area below z equals 1.5 is 0.9332. Okay, case number 2. Finding areas between two values of z with the same sign. So the first figure, they're all positive, and at the second figure, they're all negative. So what we're going to do is, after getting the value or the area from the z table, you have to subtract the smaller area from the larger area. Like this. The first value of z is number near 0, and the second number z, that is number farther from 0. So the area of the region between z1 and z2 is, we have area 2 minus area 1. So it should be greater area minus the smaller area. Okay, find the area of the region between z is equal to 1.23 and z is equal to 2.57. So we'll get their area. That is, the area of 2.57 is 0.4911 and the area of 1.23 is 0.3907. So bigger area minus the smaller area. So the answer is 0.110. Okay, the area of the region between z is equal to 1.23 and z is equal to 2.57 is equal to the area between z equals negative 2.57 and z is equal to negative 0.23. So they have the same value, so same area, that is 0.1104. Okay, find the area between, find the area of the region between negative 0.96 and negative 0.36. So again, you will subtract from the bigger area minus the smaller. So 0.3395 minus 0.1406, that is 0.1909. Okay, example, find the area between z equals negative 2 and z equals negative 1.5. So take note, they're all negative. So you have to get the area of the z table at the positive value. So number one, you have to draw a normal curve, locate the z values as the figure at the right side, and draw a line through the z value to shade the required region. So that is between negative 2 and negative 1.5. Then you can solve the z table and find the area that corresponds to z equals negative 2, which is 0.4772, and z equals negative 1.5, that is 0.4332. And the graph suggests subtraction because they have the same sign, they're all negative. So bigger area minus smaller area. We have 0.4772 minus 0.4332, and that is 0.0440. So in notation, we have the probability of z is greater than negative 2 but less than negative 1.5, that is 0.0440. And you make a statement indicating the required area. The area between z equals negative 2 and z equals negative 1.5 is 0.0440. Case 3. Finding areas between two values of z with different signs. It's either positive and negative. So what shall you do if they have different signs? So you look up both z-scores at the z table to get the areas, and you are going to do is to add the two areas. If they have the same sign, all negative or all positive, you have to subtract. But this time, if they have opposite signs, the z values of different signs, you have to add the two areas. Okay. Finding areas between two values of z with different signs. The first z is negative and the second is positive. So the area of the region between the first z and the second z is area 1 plus area 2. So you have to add their areas. After you got that at the z table, you have to add. Okay, find the area of the region between negative 2.46 and 1.55. So after getting the value of negative 2.46 and 1.55, you have to add them. So that is 0.4931 plus 0.4394, we have 0.9325. So take note, if the z-values have opposite signs, it's either positive or negative, you have to add their areas. Case number 4. Finding areas of regions to the left of a positive z or to the right of a negative z. So to find the area to the left of any positive z-score to the right of a negative z-score, okay, you look at, for example, to the left of positive z. So your graph should be going to the left. You shade it. And if we will say to the left of, to the right of negative z. So from negative z, you shade the normal curve to the right side. So what shall you do? You add 0.5 to the area. So after getting the values from the z table, you have to add 0.5. Example, we have find the area of the region to the left of z equals 2.37. So from the table, the area corresponding to z equals 2.37 is 0.4911. So since we will get the area to the left of positive 2.37, that is the value of z, so you will shade the whole region to the left of 2.37. And what you're going to do is to add 0.5 from that given area. So we have 0.5 plus 0.4911 is 0.9911. Next example, find the area of the region to the right of z equals negative 2.37. So this is negative, and we will shade the normal curve to the right of that negative number. So the same process, you have to add 0.5 to the area of negative 2.37, that is 0.4911. So the required area is 0.9911. Okay, let's have this. Given examples, determine the area of the indicated region under the standard normal curve. To the left of z equals 1.31. So from positive 1.31, you will shade the normal curve to the left. So we will add 0.5 to the area of 1.31. Next is to the right of z is equal to negative 1.92. Since that is negative, so you will shade the normal curve graph to the right. So we will still add 0.5 to the area equivalent to 1.92, and the sum is 0.9726. Number 3 is to the left of z equals negative 2. Since that is a negative number and you are going to graph to the left of that, so we will subtract the given area of negative 2 from 0.5. So the result is 0.0228. Number 4 is between z is equal to 1.23 and z equals 1.9. So they have the same sign. After getting the area, subtract from the greater area minus the smaller area. So the result is 0.0806. And number 5, we have between z equals negative 1.98 and z equals negative 1.46. So after locating their equivalent area at the Z table, you have to subtract because they have the same sign. You subtract greater area minus the smaller area. So the result is 0.0482. And number 6, we have between Z is equal to -3 and Z equals 1.5. So as you have noticed, they are opposite because negative and positive, they have opposite signs. So what shall you do is to get the area of -3 at the Z table and the area of 1.5 also, and you are going to add them. The sum is 0.9319. Okay, as a review, recall that the area under the graph of a continuous probability function corresponds to the value of a probability in an interval. So P of Z that is greater than A, that is to the right of A, and P Z is less than A, that is to the left of A, and P, we have Z is greater than A but less than B, that is between A and B. Note, the area won't change even if that greater than and less than are replaced by greater than or equal and less than or equal signs, respectively. Okay, we have the probabilities and areas under the standard normal curve. So in letter A, we have Z is greater than 0 but less than 0.33. That is the direct table value. Z is greater than 2. That is case number 1 because that is to the right of positive. And we have Z that is less than 1.67. That is case number 4 because from the positive area of the normal curve to the left because that's less than. So that's case number 4. And if Z is greater than -1.03 but less than -0.99, that is case number 2. And -2.99, that is Z is greater than -2.99 but less than 0.2, that is case 3. Okay, let's have this example. If Z is a standard normal random variable, what is the probability that Z is greater than 0 but less than 0.33? The area is 0.1293. Z is greater than 2, so you subtract 0.5 minus the area of 2. That is 0.4772, and that is 0.0228. And the Z that is less than 1.67. So since from 1.67 to the left, so you shade all the region there to the left of positive 1.67. So we'll add 0.5. And the area of 1.67 is 0.4525. And that is 0.9525 is the sum. And letter D, we have Z is greater than -1.03 but less than -0.99. So you will subtract from the greater area minus the smaller area. So we have 0.0096 is the result. In letter E, we have the Z is greater than -2.99 but less than 0.2. So negative and positive. So you have to add the two areas. So from the Z table, we have the value for -2.99 is 0.4986, and the value of 0.2, the Z table, is 0.0793. So their sum is 0.5779. Okay. Let's have here the Z is greater than -0.75 but less than 0. We have 0.2734. That is at the z table. And we have also the probability that z is greater than negative 1.92, since from negative value of z to the right, because that is greater. So the shaded region is from that negative number going to the right. So we add 0.5 plus the area of 1.92, that is 0.4726. So their sum is 0.9726. Number 3, we have the z that is less than 1.11. Since 1.11 is at the right side of the graph and less than, meaning all those numbers that is less than 1.11, so your shaded region will be going to the left. So we still add 0.5 plus 0.3665, which is the value of 1.11, and the sum is 0.8665. And number 4, the z is greater than 0.33 but less than 0.99. So we will subtract the greater area minus the smaller area. Since they have the same sign, so you have to subtract their areas. And the difference is 0.2096. And number 5, we have z that's greater than 0.2. So 0.2 is positive. And your shaded area for that is going to the right. So we will subtract 0.5 minus the value of 0.2 at the z table is 0.0793. So their difference is 0.4207. So for our integration of faith and learning, each of us have our own individual differences. We have different type of characteristics. Maybe some of us knows how to sing but doesn't even know how to dance. Maybe they're a good public speaker but doesn't have a good penmanship. Maybe they're good at giving advice or at giving small inspiration to others. Lots of thoughts came into our mind that sometimes we just say, how I wish I would be like him or her. Let's always remember that in the uniqueness that we have, it is God who designed it. For he knows that we could use and take good care of it. He normally distributed those talents and characteristics to us, and it's on us on how we should deal with it. It's what the Bible says in Psalm 139:14. We are fearfully and wonderfully made by God. His works are wonderful. Remember, we are all unique. It is not good to compare ourselves to others because we have our individual talents. So it's on us to decide on what should we do to pay him for what is done for all of us. So that's all about the normal distribution. I hope you learn many things this moment. That's all. God bless.